Okay. Jennifer, since you asked for these questions, you get to start off with giving us a balanced equation. Right on my board.
Okay, I'm on my phone, so.
You can write on your phone.
Yeah, let's see, let's try this. Let's see, edit, pen. All right. So hydrogen gas reacts with nitrogen gas. H might be a little big.
Just a little bit.
Yeah, like I said, I'm on my phone. So the screen's like super tiny and compared to my finger. If you want, you can rewrite it in smaller form. So, oh shoot, what did I do? Hold on. Oh my gosh, that's humongous. I'm sorry, you guys.
You're good.
Okay.
It's okay.
That's an arrow.
Can you actually write it a little bit bigger? I can't see it.
You're
Maybe
messing
your
with
phone
me,
screen is
small.
smaller than hers.
Oh my goodness. Okay. Okay. And then now I have to balance it out. Let's see. We have 3 hydrogen here, 2 here, 2 nitrogen. Okay, so what if we do 2? Oh. Okay. 2, so that makes 6. 3. Ta-da!
Okay. Good job. Good job. Okay, so I'm gonna rewrite it and make it a little bit smaller, if you don't mind. So that,
No, I don't think you go for it. I would not have been able to write that small. If I had my laptop, I don't know where it is right now.
you lost your laptop?
Yeah, I think I left it at my mom's house.
She knew she was gonna have Ken today. She's like, let me leave it at my mom's house.
She's like, I don't need it.
Oh my goodness. Yeah, we were putting floors at her house, and then I was like, maybe I'll try to study too at the same time. And
Yeah, we know how
I
that
did.
goes.
Yeah, no, it didn't go the way I thought it'd go. And then I ended up leaving my laptop on accident.
Okay, so we have the chemical equation, nicely balanced. Good job, good job. Leave that big N in the middle. Okay, so what is the next step?
So start with the given.
Start with the given. So we have 23.6 grams of H2.
Yes. Yes.
Okay, Vanessa, what am I going to do next?
How did I know? Okay, then you would put, there's 2 grams at the bottom of H2 and 1 mole of H2.
2 grams at the bottom and 1 mole on top.
1 mole of H2. Yeah. Oh.
Oops.
Oh, yeah, no, not the. Yeah, okay.
Will a gram mole show up on our next exam?
Just to see if you guys are paying attention. Okay, so what is that? How many sig figs?
2, or I'm sorry, 3.
So on the final, I put one question about significant figures. And one of the students come up to me and said, Dr. Henry, I don't know what significant figures are. And I'm like, yeah, you do. And no, I don't. I really don't know what they are. We've never talked about significant figures.
Oh, wow.
And I'm like, yeah, we have. And I said, sig figs? Oh, that's what that means?
And it's, Dr. Henry, it's 11.8, not 1.18.
I'm sorry, 11.8. Thank you.
Of course.
It's a day. Day's a day. Okay. Okay, what do we do next?
And then we do the 15.8 grams of nitrogen gas.
You said 15.8 grams.
Yes. And then it's 28 grams of N2 and 1 mole of N2.
Okay.
And then it's 0.564 moles of N2. Oh, 564.
Okay. And then what do we do next?
Do you need to compare them to each other?
We need to compare them to each other. How do we do that?
You take the smallest number and divide it by both of them, or no?
I wouldn't necessarily do that.
Would we do, like, for hydrogen gas, do 11.8 moles of hydrogen gas and then multiply it by, let's see, you do 1 mole of N2 over, wait, hold on. We're finding the maximum amount of NH3 product. Damn, I'm lost.
Do we
After this point.
do we add them together?
Add them together.
Oh, wait, wouldn't we do 2 NH3 over 1 N2 to get the amount of NH3 product that we'd get for that specific gas, and then see which one is the smallest, and then that's the maximum that can be produced?
You could do it that way, yes. So you're saying figure out how much NH3 we can produce for each one.
Yeah.
Okay. So how do we do that?
You would do, oh, go ahead.
Oh, do we, oh, okay, you're already on there. So then we would use our equation. So it's 1 mole of N2 to 2 moles of NH3.
Okay, so you said 1 mole of N2
to 2 moles of NH3 of ammonia.
and you said of 2 moles of NH3. Okay. And what do we get? Let's see.
We get 1.128. So 1.13.
1.13. Okay. Is that it?
But we need to do that to hydrogen gas as well.
Okay. So what is it? 3? What is ratio?
3 to 2 moles.
So 3 moles of H2
to 2 moles of ammonia.
Okay.
And then we get 7.87.
You said 7.87?
Yeah.
Okay. So which one is correct?
Would it be 1.13 moles of nitrogen would be the most that could come out?
Moles of
Is that
ammonia.
equation?
Yep. That is
Or
correct.
yeah, moles of ammonia. Sorry.
Yep. Piece of cake?
Is there
well,
any other way to do it?
well, I'm just
Yes.
confused as to why it's 1.13.
Because this is how much nitrogen you have. This is how much hydrogen you have, right? Now, if we use up all of our nitrogen, this is how much ammonia that we can produce. You need nitrogen to make ammonia. Does that make sense?
Mm-hmm.
Kristen?
Oh, is it because it's 2n in the balanced equation, and then when you're doing the dimensional analysis, it's n2, and that's why you're using all of it? Is that what you mean?
Okay, remember the bread and the cheese,
Mm-hmm.
right? Remember that? Remember when we talked
Yes.
about the bread and cheese, making a cheese sandwich?
Yes.
Okay, so this is like the bread and the cheese. So if I have 11 slices of cheese and I have 30 slices of bread, how many sandwiches can I make?
11.
Why can't I make 15?
Because you don't have enough.
Exactly, right? So this is the same concept. We don't have enough nitrogen to make all of this ammonia. Do you understand?
Yes.
So does that answer your question?
Yes.
Okay.
So will it always be the smallest number?
Yes, if you're comparing the
Okay.
products, yes.
Yeah. Okay.
If you're comparing the reagents, you don't know until you compare the products. Or
Right.
yes, but there is another way that you could have done it. You could have compared them to each other. Right? So this is one way. To me, this is the longer way. Well, it also depends on what you're looking for. So. Do you know what I'm saying? Okay. So I could have also just compared, I could have calculated how much hydrogen I produce down here and compared it to how much I actually have. So this is what I would need for if I start out with this amount, and this is how much I actually have. So let's do that. We'll do one more row. I'll make it in green. Give me 1 second, okay? Let's see. So I could have started out here with the 0.564 moles of N2. What is the mole to mole ratio of nitrogen gas to hydrogen gas?
1 to 3.
Oops.
So it's 1.69.
So this is telling us that if we start out with our nitrogen, this is how much hydrogen we're going to actually need to react, right? How many moles of hydrogen we're going to need. And we know that we have 11.8 moles of hydrogen. So then that lets us know that hydrogen is in excess. And nitrogen is limiting. So simple. At least lie to me.
Yeah. So this would basically just be like if the question was asking you which one is the excess and which one is the limiting, this would be
Yeah.
the better method to use.
Yeah. So yeah, you can use either way. You know, you can use the product as a way of determining it. And a lot of people do that. But to me, sometimes getting to that product takes a bit. And so for me, I think it's easier for me to just to compare and contrast.
The products at the end?
You can compare the products at the end. That's one way of doing it. To me, that seems like more work. I like to do it
Right.
the other way, where I get them so I'm comparing apples to apples.
But like based on the question that we have,
Yeah,
which
that
would
makes
be-
sense. It makes sense to go with the product method.
Okay.
Yeah.
Because we wouldn't get 1.13 moles of ammonia doing your method, the green method, right?
No, then you'd have to go to the next step and get it that way.
Oh.
Yeah, but sometimes you'll get questions that'll ask you about which one is excess and which one is limiting, and how much excess is the other one, and stuff like that.
Yeah, so when it asks you like how much excess you have, would you just go 11.8 minus what you got, your 1.69, then you
That
find
is
the
correct.
amount?
That's
Okay.
right. So energy. So we've talked about the law of conservation, and we've kind of been putting energy on the back burner. Now here's our opportunity to start putting energy into our equations. Okay. So, but first we have to talk about the units of energy. So the most commonly known units, or the SI units, is joules. And it's pronounced joules, not joules. Okay. I know that the spelling is odd. It's named after this guy. So, and a joule is basically equal to the force of 1 Newton applied over a distance of 1 meter. Okay. So again, this is the SI units per energy. 1 joule is equal to 1 kilograms times meter squared over second squared. Or if we think about it, it's going to be mass times velocity squared. If you look at 1/2 times mass velocity squared, that's going to equal to your kinetic energy. You may want to write this down because you may see it on your test or something like that. Okay, so a calorie. The calorie is basically the energy required to raise the temperature of 1 gram of water 1 degree Celsius, or 1 degree Kelvin. Okay, so that's a small c calorie. Okay, and the reason why I'm emphasizing small c calorie, because we have a big C calorie here that I'm going to explain in a second. Okay, so 1 calorie is equal to 4.184 joules. A kilojoule and a kilocalorie are often going to be used as well as joules and calories. So kilojoules are typically when we're using large amounts of energy. Kilocalories when we're using large amounts of energy. 1 kilocalorie is equal to 4.184 kilojoules, right? Remember, we kind of talked about that with mass, that prefix kilo, you know, kind of cancels out. So that's the reason why we could say joules is equal to kilojoules. Okay, so a food calorie, that's the calories you see on the back of your food, that's a capital C calorie. Okay, and a food calorie is going to be equal to a kilojoule. So capital C calorie is equal to 1,000 small c calorie. Okay, so guys, you need to pay attention to whether it's a capital C or if it's a small c. You got that, Kevin?
Yep.
Because otherwise, that could end up being a small c on your grade too, right? If you don't pay attention to that. Okay. So calculate the number of kilocalories, calories, and joules in 42.5 kilojoules. And let's do capital C calorie as well too. Okay, so we're going to have Jason. I don't know what name I was spelling there, Jason.
I was like, I don't remember an L being in my name, but all right.
It's one of those days. I don't know what's wrong with me today. Let's see. We'll have Hector. This is going to be Cheyenne. And this is going to be Kevin. And this is going to be Alan.
Wait, which one am I doing? It just says.
Oh, actually, you're doing the one next to it. Alan, you get off.
I can be off. Alan can volunteer.
Damn.
Okay, you can share it on the screen.
Dr. Henry, I can't write on your screen.
That was Cheyenne.
Yes.
Okay, so you're going to translate for me? What do I need to do?
Okay. Wait, so to go from kilojoule to joule, would you have to go to like calorie first?
Do you need to go to calorie?
Because
What-
when I
what does-
what
what
I
does-
wrote down,
What does kilo mean?
Kilo is 1,000, so you just take away 1,000, right?
Okay, so you're saying if we have 42.5 kilojoules,
Yeah. So then you would do 1,000 joules for 1 kilojoule?
1,000 joules per 1 kilojoules.
Yeah.
Okay, so what is that?
So that's 42,500. And then if you want sig figs, you would do 4.25 times 10 to the third.
Scientific notation, you mean?
Yeah, so that you could get like the sig figs.
Okay, so you said 4.25 times 10 to the third.
Yeah.
Okay. Piece of cake?
Yes.
Isn't that one 10 to the 4th? Because you moved it over 4 times?
That is correct.
Oh yeah, you're right. Thank you, Jason.
Yeah, I just wanted to make sure. So for mine, is it, I guess I'm a little bit confused, but I don't know. So I need to convert mine to joule first, and then
Okay.
go from joule to calorie.
Okay.
So we already converted it there with hers.
Okay.
So would it be, I'd rather just use the not scientific one. So the 42,500 joules.
Okay.
And then you would basically divide that by 4.184, which would then give you the 1 calorie.
You're saying I have this amount of joules,
Yeah,
and I'm dividing it by what?
because isn't
4.18.
4.184, because isn't 1 calorie equal to 4.184 joules?
Yep. And then 1 calorie on top.
Yeah.
Small c calorie. Okay.
And then we get with the sig figs.
Why aren't you doing kilocalories?
Oh man, yeah, I guess I am. I looked at it wrong. Okay, so then it would have just been the 42.5 divided by 4.184.
Okay. So you want me to erase this part here? Is that what you're
Yeah.
telling me?
Yeah,
So
my bad.
why am I doing all the work? Why aren't you doing the work, Jason?
Oh, I guess I could annotate.
Uh-huh.
I just wanted to see you struggling, that's all.
I see that. You're on a roll today.
Just trying to see how much I can get away with, you know?
Uh-huh.
Okay, I can take over from here. I don't want
Okay.
you to stress your index finger too much. So we have that, and then we're dividing it by 4.184 kilojoules, which would be 1 kcal. So then we get
Piece of cake?
Wait, so is the J on the bottom a lowercase j or an uppercase J?
It's an uppercase J.
Oh, okay. I thought that was a dot up there.
Yeah, he's being a slacker. He's trying to
sorry,
make it difficult.
Kristen.
It's okay.
Thanks for getting me in trouble.
Hey, that's all you did. I just pointed it out.
See how it is.
Okay, Hector. Are you there, Hector?
Yeah, I'm here.
Okay.
Give me a sec. I'm still trying to figure it out.
Okay.
Dr. Henry?
Yep.
I had a question. Why is it that 1 calorie and 1 kilocalorie is like it's the same number except for it's like kilojoules and joules?
So 1 calorie make sure I do this right. Over 4.18 at 4 calories. I mean, joules.
Mm-hmm.
Is this what you're asking me? I want to make sure that I understand the question.
Yeah, pretty much.
Okay, because kilo, right? That means 1,000, right? So we would just basically multiply this by 1,000 and this by 1,000.
Mm-hmm.
And so you have 1,000 over 1,000. What does that equal?
Oh, 1.
Okay, so then it's just going across. Long as those units on top and the units on bottom, or I should say that prefix on top, the prefix on bottom match, then it's going to be equal to that same conversion factor.
Oh,
You
okay.
get milli, 1 millicalorie.
And then it'd be 1 millijoule.
It's going to equal to 4.18 millijoules.
Okay.
And if I did mega,
Same thing. Got it.
Yep.
Okay, that's convenient.
Yep. Is that correct, Hector? Doesn't it equal 1 kilocalorie?
Not sure.
It's right up here. So 1 kilocalorie is equal to 4.84 kilojoules. So then how do I change? So this should be a K here. How do I change kilocalories to kilojoules? I mean, kilocalories to calories. How many calories are in a kilocalorie? Hector. Kilo.
1,000.
1,000. So we go 1 kilocalorie to 1,000 calories.
Dr. Henry, for the conversion of small calories to big calories, what was that? I missed it.
So 1 big calorie,
Okay.
capital C calorie,
Yeah.
is equal to 1,000 small c calories.
Okay, so 1 big calorie
Or you could say 1 kilocalorie.
is equal to
So capital C calorie is food calories.
okay.
How do we know which ones are capital K's in here or not?
Kilo technically should be small, lowercase.
Oh, okay.
But you'll see sometimes in the book they'll even use capital K. It really should be a small k.
And we haven't gone over the capital K, right?
The capital K, no, we have, well, we've gone over Kelvin only, which
Right.
is a capital K, but
But not
Yeah,
like what
there's-
we're doing here.
yeah, not for a prefix, no.
Oh, okay, got it.
Good job, everyone. Questions, concerns, cash. And don't forget your units, Hector. That's a -1 point on the test. Ouch. Okay, you guys have any questions?
No, I'm just trying to write it down. Don't take it away yet.
So like, for example, for like, do we not care about sig figs at all?
Yeah, we do. So we should have sig figs. So we should have done sig figs here. What is it, 102? Stop picking on Hector.
I just wanted to make sure I don't get anything wrong.
Okay, questions, concerns, cash. Preguntas.
Are we still going to go over the lab today?
Yes, that is the plan.
Tonight or?
No, we're gonna try to do it here
Okay.
right after one more question.
Okay.
Okay, can I clear it?
Mhm.
Yeah.
Yeah, that's why we're only doing this chapter.
Thank
We're not
you.
doing the next one. Okay, so thermochemistry equation basically take into account the energy, right? And energy is a form of, it can be a form of heat, you know? So often we'll use the term enthalpy. Enthalpy means like the heat of the reaction. So it's basically the energy that's in the system, okay? So now if you're putting heat into a system, that's going to be endothermic. And then the value of the enthalpy is going to be a positive value. And you guys remember what endothermic means, because we talked about that at the very beginning. You guys remember?
Yeah,
And then exothermic must mean what?
you're releasing heat.
You're releasing heat. Okay, so let's say we're having a bonfire. So is that endothermic or exothermic?
Exothermic?
Exothermic.
Okay,
That's a felony right now.
I'll put that on my slides.
Only for 2020, hopefully.
Okay. Okay, so I'm going to show you two ways, or basically you can see on the screen, two different ways of showing how to write the equation, okay? So the first way is where we write the equation and then we put the enthalpy on the side. It's kind of like a la carte, you know, so it's independent. Okay. Oops. And then the second way is that where we actually integrate the enthalpy into the equation. And so in this case, this is an exothermic reaction. So our value is going to have a negative value if we put it a la carte on the side. That lets us know that energy is being released if it's a minus value. The way that we would write it, so that we part of the equation, is here we have C2H6, gas, plus 7O2, gas, yields 4 carbon dioxides, gas, 6 waters, and that value for enthalpy. But if you notice, it's plus 2,855 kilojoules. And it really should be 2,855 kilojoules per mole. Okay. The reason why they don't say it's per mole, because we have to actually divide this by that molar value so that we would be talking about a single unit of whatever we're burning. So in this case, we'd be talking about 1 unit of C2H6, and then we'd have to divide everything by 2 to get it per mole basis. Do you guys understand that? Or was that kind of weird? You can say it's kind of weird. It's okay.
It's kind of weird.
Kind of weird. Okay, so let me rewrite this equation for you, so it would actually be correct. So when we're talking about enthalpy, right? We're talking about. Do you guys remember? I think we kind of brought this up when we were talking about the particulate or a particle versus molar. Molar we can have halves, where a particle we can't have halves. Do you guys remember that?
Mm-hmm.
Okay, so these are based on molar quantities. These are not based upon particular quantities only, right? It's based upon the molar quantity. So in this case, we could actually have halves. So in this case, we could have C2H6 gas plus 7 halves O2 gas yields 2 CO2 gas plus 3 H2O. And then we'd also divide this value by 2. I don't know what it is off the top of my head.
You said when it's a negative, right? It's a exothermic reaction.
If it's a negative value, it's an exothermic reaction. If it's on the product side of the equation, it's also an exothermic reaction. But this is just the same equation, just written 2 different ways.
Got it.
Okay, so normally you're going to see it written in this fashion, so that it's based upon 1 mole of, in this case, this is ethane. Okay, so it's based upon 1 mole of ethane. Okay, rather than you're talking about the 2 moles of ethane burning. So usually when you see thermochemical equation, it's always based upon 1 mole of something. Okay. Okay, so here, this basically is showing you the decomposition of ammonia into its elements, and this is an endothermic reaction. And so in this case, you can see that we put the heat or the energy on the reactant side of the equation. So that means you're putting into the equation, that means it's endothermic. right? Rather than up here, you're taking it out of the equation because you're getting the product out of the equation. It's exothermic. Do you guys see me? You understand?
Yes.
Okay, good, good. Okay, so the thermal decomposition of limestone solid calcium carbonate, CaCO3 solid, to lime solid CaO, S plus gaseous carbon dioxide, CO2, is a endothermic reaction requiring 178 kilojoules per mole of calcium carbonate decomposition. Write the chemical equation into two forms. Let's see.
Can you go back to the other one so I can take a snapshot really quick? I didn't finish writing it all down yet.
Okay.
Thank you. Appreciate it. We're good.
No problem. Okay. Let's see. We're going to have Brian and Steve.
Yeah.
Okay, so you're going to write the equation with the enthalpy on the side. And then Steve, you're going to write the equation with the enthalpy incorporated into the chemical equation.
I'm still kind of lost on that, but
First off, is it an endothermic reaction or is it an exothermic reaction?
endo.
Endo. So is it going to be a positive number or is it going to be a negative number?
Positive.
Positive. Okay. So you have delta H equal 178 kJ per mole. Now, what does the chemical equation look like?
CaCO3 S.
CaCO3 S.
Yeah. And then the yield. Wait.
Oh.
The yield sign.
The yield sign.
Then CaOS. Or the solid, my bad. Then plus CO2 gas.
Is it balanced?
Yeah.
Okay, that's it.
That's it?
That's all.
All right.
Okay, Steve. What are you going to do differently?
So mine would be with it inside of the equation, right?
That's right.
So what I have to do or put it in with, so it's going to be CO3 solid. Then would it be plus 178 per kg? And then the rest of the equation from the top.
Piece of cake?
Yeah.
I had a question. Since it is endothermic, why would the 178 be essentially in the product side, not the reactant side?
It's not on the product side, it's on the reactant side. You see?
Oh, because it's just a
Yeah.
okay.
Okay. Any other questions? Okay. Okay. So at this point, this is the schematic of all the things that you guys know, right? So if we know the amount of energy, we can calculate the number of moles. We can calculate how much product we're going to be producing. We can calculate how much energy is being released. So just by using that mole to mole ratio, because everything is going to be based upon the mole. If we go back here, remember this equation here? These are kJ per mole, even though it doesn't say it in that little thing. These should be per mole, right? So if I have 0.25 moles, I can calculate how much energy is going to be needed to get this reaction started, right? Do you guys understand?
Yeah.
So if it's also 0.25 moles, I can use this to sit there and calculate how much CO2 I'm going to make. Because again, it's like a mole to mole ratio. You guys get that? So let's say if I have, so how much CO2 can I make with what I just did. Can I make with 1.78 kJ kilojoules of energy I guess I should put the words that I'm just running over. So if I'm given the amount of energy, then I would just start off with that, right? So then I can go 1.78.
You mean CO2 or just CO?
CO2, sorry. And then I just go my mole to mole ratio, 1.78 kJ for 1 mole. And that's based upon this, since this is the 1 mole of it. So Ca, CO3. And then it's a mole to a mole of CO2. Oops, see. 1 mole CO2. Oops.
Question, why wouldn't we just be able to go straight from CaCO3? Like instead of putting CaCO3, just put 1 mole of CO2?
You could in that case, but not all the time. Let's say, not in every case will it be based upon the CO2. It just happens that they're 1-to-1 right now. You understand?
Mm-hmm. Yeah. So then should we always start with the doing a conversion factor with what's in the reactant side and then do another conversion to the product?
It depends if the equation is based upon the reactant side or if it's based upon 1 mole of the product side. So typically this guy is based upon 1 mole, right? So it'll be 1 mole of something. So in this case, we're fortunate enough, it could be 1 mole of the calcium carbonate, or it could be 1 mole of CO2, right? It could have been either one, right? So, but usually one of them is designed so it's based upon 1 mole and the other one isn't. Or it may be, just happen to be, but.
Yeah.
Do you understand?
So if, for example, CaCO3 was, are we going to do other examples?
We'll do another example.
Okay. Okay.
Yeah.
Thank you.
Okay. So do you guys get it? What is that? 0.001. All right.
Yeah, the conversions make sense. I guess I'm just trying to wrap my head around why CaCO3 was used.
Get carried away with my zeros. Okay. Is that good? Okay. So what is the mass of liquid n-octane C8H18L as a component of gasoline must be burned to provide 9.505 times 10 to the 4 kJs of heat. And here they let you know that your delta H of the reaction is equal to negative 5,471 kilojoules per mole of octane. So what are we going to do? Anyone?
Do we write 9.05 times 10 to the 4th kilojoules?
First thing that I would do personally, I would always try to balance the equation.
Oh, right.
Although, but a lot of the information that you need is already given to you, but I would always try to balance the equation. So what does this a balanced equation look like for the burning of octane?
Would it be C8H18 plus O2? And then it yields CO2 plus H2O?
Okay. Is it balanced?
No.
What do I need to do to balance it?
You would put a 9 in front of the H2O. Oh, no, the H2O, not the 9, not the O2.
Oh, sorry.
And then an 8 in front of the CO2. So I'm trying to do this in my head. And then would it be 25 over 2 for the O2?
Is that too many?
Oh, no.
Let's see. No, you're right. 16.
Wait, yeah, right.
16
Yeah,
plus 9. Yep.
yeah, sorry.
Okay. And in this context, we can leave it like this. So you're saying that for 1 mole of octane, you're going to need 5.5 moles of, okay? And then your delta H is going to equal negative 5,471 kilojoules per mole. Okay, so what are we going to do now?
I had a quick question.
Yep.
Is it when it's exothermic that we have the delta RH instead of just the...
Nope.
Oh.
No, the delta RH, where it says we say delta RH, you're just saying that it's okay. In this context, delta RH is just, it can be done independently or on the side, or it can be integrated into the equation. We could have actually put this into the equation, right? And if we put it into the equation, we would have wrote it like this. And it's the same thing.
Oh,
you understand? So there's just 2 ways of writing it. That's all it is.
because I saw the last one, it didn't have an R on there. It just had the triangle and H.
So delta R just means reaction, right? And so a lot of times they'll just put delta H, which is just the enthalpy of reaction. It's understood.
Oh,
yeah.
Okay.
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 So this means that it's endothermic, the negative value, right? So we could have written it like this. I mean, endothermic, exothermic. The negative value means it's exothermic, where the positive value means it's endothermic.
Right.
Okay. Okay, so what are we going to do? What are we going to start off with next?
So now we start off with the kilojoules, right?
Yep. Okay, so we have 9.05 times 10 to the 4 kJ. Okay, so what am I going to do?
Do we put the negative 5,471 kilojoules at the bottom and 1 mole of C8H18?
So, but you're not going to put negative, right? Negative is just letting us know that on which side of the equation it's on, right? And so that it's an exothermic. So you're just going to put 5,471 kJ at the bottom. You're right. And 1 mole on top. And that's C8H18. And that's what we're looking for. We have to change the mass. So how do we change the mass?
We find the molar mass.
Okay, what is the molar mass of n-octane?
So it's 12 times 8. So it's 114.
Okay.
Grams of, oh no, in 1 mole of C8H18, it's 114 grams of C8H18.
Okay. what do you get?
We get 10.4. And then would that be in grams?
Yep.
Okay. Grams.
But is you sure you're getting 10.4? Because I get.
Oh, I didn't put. Okay, yeah, I missed. There wasn't a 9 in my thing. Okay, yeah.
So 1.89 times 10 to the third grams.
Yes.
Everyone else here?
Yeah.
Good. Piece of cake?
Yes.
And that's it. It's just like everything else. So it's just like using that mole to mole ratio. That's it. Not too hard, right?
Mm-mm.